So thanks for the introduction. So I'm going to be talking about the connected spectral form factor and especially how it relates to hydrodynamics. If you don't know what some of those words mean, don't worry. The first half-ish of the talk is going to be review. I'd like to thank the University of Maryland, my home sweet home, for housing me while I did this research, and also for this handsome fellow, Brian Swingle, for advising me and collaborating with me on this research. So a rough plan for the talk. It's going to be based on a paper whose name is roughly the same as the name of the talk that Brian and I put on arXiv last December. We're going to start by reviewing various well-known, although not as well-known as they should be, properties of spectral form factors, and especially a certain region of the SFF called the ramp. Then we're going to talk about how almost conserved quantities affect the ramp. Then we're going to zoom into a certain important class of almost conserved quantities called hydrodynamic modes. And then I'm going to pontificate about how this is the dawn of a new era for hydrodynamics. And by the way, feel free to interrupt me with questions or comments about how cool I am or anything like that. So first, I have a little cartoon here that illustrates an important property in random matrix theory called level repulsion. So these are two histograms. One of these is, I believe, a 5,000 by 5,000 matrix. I had a computer diagonalize it and plotted the eigenvalues. And the other is 5,000 randomly selected, independently selected numbers. Does anyone want to take a guess as to which is which? Come on, be brave. Really? Nobody? Okay. So the one on the left is the eigenvalues of a random matrix. And I just want to point out to you how smooth this is and how, if you have 60 samples per bin, then just sort of from the Poisson distribution, you'd expect the variation in each bin to be around 8, which is indeed what we see when they're selected independently. But because of level repulsion, there is no compressibility, there is no fluctuation in density. It's just an incredibly smooth curve. And oftentimes, when you're reading some paper about, some famous chaotic system like the SYK model or whatever, they're going to have a plot of, a energy density histogram like this. And you'll always notice, wow, this is an incredibly smooth histogram. And there's a scientific reason for this. It's because the energy levels in a matrix repel. I'm going to give you just a quick intuition for why, which is if you have a 2x2 matrix, then there's like 3 possible terms that can split the degeneracy between the 2 energy levels, right? There's sigma x, sigma y, sigma z. So to have 2 energy levels be close to each other, you need fine tuning of 3 different numbers, assuming it's a Hermitian matrix. So there's kind of these, it's like an entropic force almost that forces these energy levels not to be close to each other. It's called level repulsion. It's called spectral rigidity. You can go and figure out that it has similar physics to a Coulomb gas. A lot of people throw that word around. And this has been known, since the dawn of random matrix theory, but it's a very cool fact. So the spectral form factor, different people define it slightly differently, so I thought I'd be pretty explicit here. So we're defining it in terms of some time t and also some filter function f, which allows us to look at a given energy range. And it's the trace of e to the IHT f of h. So if we just set f to 1 for now, this is an imaginary temperature partition function. Or sorry, the z is the average temperature partition function. The SFF is the disorder average of the square of the absolute value of z. Okay, does that, everyone get the order of operations there? So I here made a graph of the SFF for pure random matrix theory. It has three famous regimes called the dip, the ramp, and the plateau. So the dip, it starts off, Z is just going to be the size of the Hilbert space. So we start off Hilbert space size squared, and then we go down. There's a little bit of a ringing effect here, which comes from the fact that the density of states is not an analytic function of E. And all of that is just stuff you could predict, even if you knew nothing about random matrices and had just seen this graph. And then we get the ramp, which is the most, at least to me, the most interesting region. And that's where the SFF starts going up again. Now, if we looked at Z is not actually going to be increasing. Z is random and not well averaged here. But the square of Z, the disorder average of the square of Z goes up until eventually it reaches a plateau value.
So Mike, just a question. So maybe you'll talk about this, but is this just a schematic, or is this actually the calculation for a particular model that you're showing?
Yeah, this is a graph, 100 by 100 GUE random.
Oh, sorry, I didn't notice that. So in general, for a different problem, the ramp onsets after the Thouless time. I mean, are you going to talk about all this stuff, or?
Yes, I am.
Okay,
I'm going to
so then I'll hold on.
Time.
Okay, so then I don't need to ask this question later. Now, sorry.
Yeah, and in particular, I think different people use different definitions of Thouless time, so I'm going to be very careful about that. We have a whole slide about how to define Thouless time. So a good intuition for this SFF is it's measuring the jaggedness of this graph here as a function of histogram width. Like it's just the roughly the sums of the squares of the height differences between adjacent bins here. So at really short times, which corresponds to really wide bins, everything is in one bin. So it's obviously very jagged. And then as we zoom in, we get something like this, way less jagged. And then as we zoom in incredibly detailedly, all the bins have either 0 or 1. And the jaggedness is just determined by the total number of energy levels, and that's the plateau. But it's this ramp, which is the intermediate stage, which is really interesting. For a review, there's this one paper with about 1 million authors you can find on arXiv, which goes over all this stuff in great detail. And I also want to talk about the connected SFF and the disconnected SFF. So we're looking at a disorder average of a square. You can always break the average of a square into the square of an average plus variance, aka the disconnected bit plus the connected bit. And so here the orange curve is the just the connected SFF. So you can see it has the ramp and the plateau, but it doesn't have the dip. Right, so the dip is driven by this incredibly non-universal, right? It's just whatever the partition function is. Partition functions are beautiful, but they're not universal. And it's the ramp and the plateau that are more universal RMT behavior. Oh, I was just saying what I was going to say on the next slide. So starting at the Thouless time, we're going to have this sort of universal ramp. The formula for the ramp is just this crazy formula, which has definitely been known for a while, but I think not enough people are going around talking about how crazy it is. So we have this integral, which is basically just integral f of squared, and then t is the time, and then beta is like 1 or 2 or 4, depending on whether you have time reversal symmetry and stuff like that. And one thing that is conspicuously absent from this integral is any real reference to the density of states, right? So we care whether there's a non-zero density of states. Oh, by the way, this is just for chaotic systems, right? What I've been talking about is for chaotic systems and systems like random matrices. I should have mentioned that more explicitly. So for random matrix-like systems, the density of states doesn't really matter for the ramp, and that is crazy. Right? We're so used to partition functions being dominated by the region with the most density of states. And we're so used to everything in physics being dominated by, maybe not the region with the most density of states, but some sort of compromise between most density of states and low energy or something like that. And here the density of states just doesn't matter at all. So the phrase I have been saying since election day is SFFs are like the Senate, not the House. It doesn't matter how densely populated you are, it just matters how big the region is. And that's what determines how much you contribute to the SFF. So do people have some appreciation for this formula and why I find it so strange that density isn't more prominently featured? Okay, I'll take that as a resounding yes. So one other thing I want to talk about real quick, just to give some more context for how crazy SFFs are, is this whole wormhole solution story. So this is one of my all-time favorite papers. It's a semi-classical derivation of the ramp for the SYK model. I want to point out how weird it is that you can do this semi-classically, since the SFF is like the ramp and stuff are very much about energy levels and level repulsion and stuff like that, which are incredibly quantum effects. But they go ahead. If you're not an SYK expert, don't worry, it's not particularly important. But if you are, what they do is they say that the SFF is equal to the partition function on this weird weird contour, which is two disconnected circles, real Lorentzian time circles, period t and minus t. One of them is going forward in time, the other is going backward in time. And they do their SYK analysis on this circle, and they show there are a few different solutions to the mean field equations. So we start off with two different copies of time translation symmetry, right? We can translate the left or right replica. And they show that one of the solutions, particularly the one that dominates at later times, spontaneously breaks this symmetry. So we now, this time has to map to some specific time here, can map to any time. And so the manifold of solutions of size proportional to t, and that's where the t comes from in the ramp. And if you go through their analysis in more than one slide, you can get this exact formula, basically. So here, they get the disorder average SFF. But this sort of knocks against one of the crazier aspects of SFFs, which is the SFF, especially the connected SFF, is a weird quantity. Right? It's inherently a disorder average quantity. And this runs up against a lot of, I don't know what it is, drama or tension or confusion in the holography community, because we have all of these gravity theories where you just have a single theory that's dual to a ensemble of CFTs. And the SYK model is a great example where you have this ensemble of disordered systems that's dual to JT gravity. And so if you do the calculation in JT gravity, you just get the disorder averaged answer here. JT gravity doesn't really factor because you can have wormholes. Whereas if you just had a single microscopic quantum field theory here, the answer would just be the answer on this loop times the answer on this loop. It would have to factor. This is a mysterious thing that we as a species are only partially understanding, and I just want to mention it. It's not really relevant to the rest of the talk, but it is confusing and fascinating. Okay, and then the one last sort of preliminary thing I want to get over is arguing about the definition of the Thales time. So different people define it different ways. I don't mean to harsh anyone else's definition, but the definition we're going to use is when the connected SFF starts looking like the RMT, the random matrix theory universal answer. So it doesn't have anything to do with the disconnected SFF. It's just when does the connected SFF look like random matrix theory? So are people following what I'm saying so far? Okay. Oh, one more thing.
Wait, actually, could you please go back to the previous slide?
Sure.
So, I mean, the spectral form factor has been even studied in the past in mesoscopic systems where, sorry, did you say something? I missed it.
I was just agreeing, yes.
Okay, sorry, I missed that. And so, first of all, I mean, I guess you don't really need, I mean, you can define it even for a perfectly clean system. like the definition doesn't necessarily require you to have
Sure.
order averaging built in. But so there it's related to the diffusion coefficient and system size.
Yeah.
But I guess, is there some limit where your definition is the same as what people are used to in the context of mesoscopic systems, or does it lead to something different?
So my definition will agree with what you said. Again, it just agrees. It is, my definition is going to have to do with the diffusion constant for mesoscopic systems. Where there's an issue is here. I want to be clear that the Thales time is here, not here. Can you even see my?
Yeah. Okay. Good. Okay. Thanks.
Okay. Yeah. Okay. So I just want to talk also about Hamiltonians with sectors. So the easiest way to have sectors is just to have a conserved charge, but also we've been thinking a lot about spin glasses. So I have a ton of backup slides about that. So for now, just think about a conserved charge. So the Hamiltonian will not have any terms that connect charge equals 1 states with charge equals 2 states or whatever. So there's not going to be any level repulsion between charge equals 1 and charge equals 2. This is going to lead to enhancements in the fluctuation in the density of states and a corresponding enhancement in the ramp. One way to look at it is just each sector is going to have its own ramp. Each charge level is going to have its own ramp. So the formula gets modified a little bit to just have a factor of the number of different sectors. Okay, so this has all been reviewed so far, halfway through. Now we're going to get to the cool stuff. What happens if we break our conservation law a little bit? There's a lot of physical ways this might happen, of course. I'm going to get into some of my favorite ways later. And Brian and I derived a formula. And basically, there's an enhancement by this sum here. The sum over all sectors of the probability of being in that sector after time t. So just to give it a little bit of intuition for this quantity, for small time, the probability you're still in a given sector after time t is just going to be 1. So it's just going to be enhancement by the number of sectors, which is what we had in the previous slide. For long times, the return probability is just the equilibrium probability. So this sum is going at, I can't highlight the sum. So this sum is equal to the sum of the equilibrium probabilities, which is just going to be 1. So the enhancement factor is 1. That means we've reached random matrix theory. So there's this sort of clean statement that we reach random matrix theory exactly when the system thermalizes, right? The enhancement factor from random matrix theory becomes 1 exactly when the distribution equals the equilibrium distribution, which is a nice way to calculate Thales times for arbitrary crazy systems. Does this make sense to people? Okay. So here are just some graphs in case you didn't trust me on the previous slide. We made some toy models, just various random matrix systems coupled to each other, and graphed. We used Fermi golden rule to figure out the transition rates between them. And then we graphed the realized enhancement factor versus the predicted enhancement factor. And you can see the blue lines and orange lines. I don't know if you can even see there's 2 different lines because they line up so well because the theory agrees with our numerical experiment. And we tried it, bunch of different ways of coupling, different size sectors, same size sectors, all sorts of different equilibrium distributions here. And it always works, and it should always work because we have an analytic proof of it in our paper. But if you're like me, you trust things more when you've actually seen them in a pretty graph. So that's what this is. Okay, so now let's see how this ties into hydrodynamics, the really cool stuff. So hydrodynamics has been around for however many thousands of years since Archimedes. But the sort of modern philosophy of it is it's the study of slow modes, and especially slow modes guaranteed by conservation laws. So my favorite example is like it takes a decently long time. Like, so the total amount of energy in a closed system is conserved. A total amount of energy in an open system is not conserved, but it does vary sort of slowly. Like, right, it takes the relaxation time is proportional to L squared, as we all learned in undergrad or whatever. It can take a while to relax. So we can use this to define an almost sector, right? It is the overall energy is exactly conserved, and the energy in, my room, the energy in your room, the energy in, Steve's room or whatever are all almost conserved, slowly relaxing quantities. So now we want to calculate the sum over all the return probabilities, right? Each sector is characterized by like an energy profile, if you will. We want to figure out the sum of return probabilities for over the space of energy profiles, which is a technically kind of daunting task. But luckily the tools exist to do this. So I'm gonna go over or review how those tools work really quickly. There's a whole universe of fluctuating hydrodynamics and people studying how to do this. My formulation of choice is the CTP formalism. My favorite review is by Paulo Glorioso and Hong Lu, but zillions of other people have been working on this, including Mike Crossley and Mike Blake and Sasha Grozdanov. And I'm going to stop listing because at this point, people should be offended if I forget them, but tons of people have worked on this. So this is hydrodynamics on a Schwinger-Keldysh contour. For those of you who don't remember what that is, it's dynamics on a complex contour. We have a thermal circle here, then a forward and backward contour. We have two copies of every field. We have one on the forward contour, one on the backward contour. And it's traditional to redefine them in terms of phi r and phi a, the symmetric and anti-symmetric combinations. I believe it stands for retarded and advanced. And you can go and show pretty easily that the action is always proportional to each of the A-type variables. If you're working in terms of the bare microscopic fields, it's of course just going to be action on this contour minus action on that contour. But once you start integrating out microscopic fields, you can get a more complicated action. So that's a quick review of Schwinger-Keldysh. Let's practice with a Schwinger-Keldysh theory of Brownian motion. So here we have a Lagrangian, which describes mean reverting Brownian motion. We're interested in some sort of, if we're interested in some sort of endpoint function of this, well, first of all, this is a pure quadratic theory, so we only need really the 2-point functions. And second of all, there's a theorem called the last time theorem, which says that the chronologically latest insertion is an A-type variable. The endpoint function is always going to be 0. And if we look back here, that's because we have a phi 1 here and a phi 2 here, and we're subtracting them. But phi 1 and phi 2, if it's the last time, are equal as an operator identity. So the difference is 0. That's where we get this last time theorem. And then we can go ahead and just invert this Lagrangian and get the 2-point functions. And they're sure enough exponentially decaying and everything. Do people have any questions? Okay. So now let's go ahead and calculate the sum of return probabilities. So everything is still Gaussian. It's often convenient to introduce an auxiliary field here. This is still the same path integral. We just introduced another field. So now XA is a Lagrange multiplier forcing the particle to have a certain equation of motion. And we can figure out the probability distribution as a function of the initial position. We get this Gaussian thing. We can do the integral, and we get this factor here, 1 over 1 minus e to the minus kt. And we can also get this result by just straight up evaluating the determinant of this Gaussian integral, which is kind of a cool fact. And it's going to be useful once we want to start doing lots of these. So do people understand so far? Okay, so now we're going to go to a more complicated version. So now it's phrased in terms of phi a, and then epsilon is just the energy density. And if we go into the Fourier modes, we still have roughly the same equation, and we get a product over all the modes for our enhancement factor. And this is an infinite product, but luckily we can evaluate it, and we get this quantity here. And it turns out we are not the first people in human history to get this quantity. Some other people were calculating the SFF of a Floquet system, so not quite the same thing, but a Floquet system with diffusive, with a conserved charge, and they got the exact same answer. And so just for fun, we can do the same thing for subdiffusion, and we can also get this answer. And once again, a similar set of people have done this calculation for a Floquet system, and again gotten the same answer. So these aren't new results, but they're old results being derived in a much more, in a newer, in my view, much more compact and efficient way. Right. Once we have all this machinery down, it's just a couple lines to get these quantities, which is very cool. But we can do more. Right. So far we've been working in purely quadratic theories, but we can actually do perturbation theory in this weird hydrodynamic setting. Before we do that, I just want to go over how the 2-point functions are going to change once we have periodic boundary conditions. So when we have periodic time, the last time theorem doesn't make sense anymore because there is no last time. Time is periodic. So we get a different expression for GRA. We also have a different expression for solving GRR on this contour, but GRA I think is more striking. So I tried to have a drawing in order to illustrate it. So blue is a graph of GRA for positive time and negative time. And then these other graphs are just sort of supposed to illustrate how it's the sum of all these exponentially small echoes. And I'm not sure if anyone's actually gonna get that here, but if not, just here's the formula for it. So does everyone either understand the graph or understand the formula? Okay, I'll take that as a yes. So now we can do interacting hydrodynamics. We can throw in non-quadratic terms into our Lagrangian. And something kind of new and surprising happens because in the old version of hydrodynamics, you can go and show that every bubble diagram evaluates to 0. And the quick way to show that is every term in the Lagrangian has at least one a variable. So that means there has to be at least one propagator where the a variable is chronologically last. And we've already decided that means the propagator is 0. So every Feynman diagram is 0 in Schwinger-Keldysh. Every bubble diagram, vacuum energy diagram is 0 in Schwinger-Keldysh hydro. But with this new periodic time, there are new classes of diagrams. So here I drew one, which we evaluated and got that it's the dominant contribution for 1D at low times. So for short times in one dimension, this can send you from diffusive to subdiffusive, which is kind of interesting. And yeah, more broadly, there's tons of diagrams that can have effects at various orders in perturbation theory and in various settings. So now the temptation is just go and redo all of hydrodynamics in this new context, right? So there's superfluids. Brian and I started here. We have a paper that came out a few months ago. Someone is calling me on a phone. Yeah, we have a paper that came out a few months ago looking at spontaneous symmetry breaking hydro. We definitely did not figure out everything there is to figure out about it, There's sound, how does sound affect us? There's this whole universe of magnetohydrodynamics and higher form symmetries. How do they thermalize here? There's phase transitions and fluid gravity correspondence. And all of these things we can do in this new periodic time context. Now I just want to talk about the, hopefully the key takeaways you've gotten here. So I want to point out, I want you to remember that the ramp for almost sectors is enhanced by the sum of the return probabilities. And in this way, spectral form factors provide a link between spectral statistics and this quantity that really is just a measure of equilibration. I want you to remember that almost sectors are just really another way of saying slow modes, especially in the context of hydrodynamics. So we can use hydrodynamics to calculate this sum for all sorts of different systems. So that's everything I really wanted to say. I have plenty of other things I can also say, but I think it's time to open things up for questions.
I mean, are there any questions or?
Yeah, can you explain that plot again? The one with this many spikes on top of them, on top?
This one?
Yeah.
Okay.
Echoes.
Okay, this was my attempt to convey the idea. So basically, we have our Lagrangian. We're trying to invert it on a periodic time fold. And this is my attempt to convey how that works. Right, so we want to invert this Lagrangian here, basically. So it's like a delta function, and then it decays, but it's periodic. So like there's a delta function, and then you're decaying, and then these other things are like showing how it would keep decaying if you didn't continually hit it again and again, because it's periodic time, so you keep getting sourced again and again and again, is what I'm trying to convey here. But it might just be easier to, invert it yourself because it's just a differential equation, and then try to understand my artwork.
But there was a physical. I thought you gave some physical intuition for what these, in terms of echoes or something. What?
Yeah.
What am I supposed to think?
So what's happening
physically going on here?
Let me try to write some equations. Right. So so we're inverting. We're getting the 2-point function for a quadratic system. We're just inverting the Lagrangian, and right. So the we have, how do I write something? Right, so something like partial t minus k g equals delta function, right? That's just the formula for 2-point function. But we're on a periodic, not lattice, we have periodic time now, right? So like there's going to be effectively a source of time 0, and there's a source of time t, and a source of time 2t, and a source of time 3t, and a source of time minus t, right? Because of the periodicity. And that's what I'm trying to say by echoes.
Okay, it's basically sum over images. You're finding the Green's function.
Yeah. Sum over images is a good way.
Okay, thanks.
Yeah, it's just a trick to evaluate the 2-point function. Where'd the old thing go? Okay.
I mean, if there are no other questions, you can just keep going, I guess.
Okay, yeah. So other stuff I wanted to talk about, which was exciting me recently, is the connection to spin glasses. So we have not quite finished writing this paper, but I'm excited anyway, so I'm going to tell you about it. So for those of you who don't remember what a spin glass is, a spin glass is a system with many degrees of freedom and with chaos, but which doesn't thermalize. And the reason it doesn't thermalize is because there are high energy barriers between various low energy states. So the simplest system that you could possibly call a spin glass, I feel reluctant to call this a spin glass, but the thing you should have in mind is a ferromagnet, where there's the up states and the down states, and it's very, very hard to tunnel between the up states and the down states. So in a certain sense, it's not thermalizing, right? So a spin glass is something which, instead of having those two low-lying regions of phase space, has tons of low-lying regions of phase space. So it has a lot of trouble thermalizing. And there's exponentially many disconnected regions of phase space. And we can think of all of these different regions that don't thermalize as the sectors in an almost conserved Hamiltonian. And so we went and we've evaluated using path integral methods the spectral form factor for a certain class of spin glasses, and we've gotten that it's equal to various known results for the number of quasi-sectors. So that's like a nice nice connection there. And what's especially interesting is this this sum of return probabilities quantity here was already in use by the spin glass community as a good definition for how many low-lying, how many sectors are there, because it can be hard to count it, and this was already in use. So he felt sort of proud of that, to have made a very clear connection to an existing tenet of spin glass literature. So yeah, that's one thing we were excited about. We're also we're working on sound poles and how the SFF works when basically when this K becomes imaginary, or equivalent, I guess, where this K becomes imaginary. So now you can be multiplying up all these, some of these enhancements will now be decreasing it, some will be increasing it. And so it can be very, very tricky to even evaluate the analog of this product. And you're going to get that this product is itself disordered. And in fact, this product is equal to the SFF of an emergent system, which is like kind of meta, mind-blowy. So we're still working on that, but we're very excited about that too. That's no one has any questions about any of this. I just explained it all perfectly.
Can I ask a question?
Okay, great.
So using this formalism, do you have an intuitive explanation why the quadratic SYK model has an exponential ramp? Oh yeah,
yes, that's a different paper that Xiaokai and I wrote, and yeah, it has a very nice explanation. I don't know, how's your SYK knowledge? So it's basically, if we go back to this thing, the wormhole solutions, the idea is it's the same thing, except the spontaneously broken group isn't the time translation group. It's the group of all SU2s acting on the two replicas at different frequencies. And so the longer the time is, the more different frequencies there are. So you have more and more spontaneously broken SU2s. And so the phase space volume you integrate over becomes exponentially larger. So that's why you get an exponential ramp. That's one explanation. There's also a comparably cool explanation, although totally different explanation, which is, so it's a non-interacting system. So if we want the SFF, we can just multiply the SFFs of each of the different fermions. Let me try to write this down here. So it's product over all the E's of one, what is it, plus E to the I E T, where E is the microscopic energy of the fermion, right? And the E's themselves are coming from a Wigner semicircle distribution. So if we do the disorder average of this, we're going to get, this is equal to the exponential of, sure, this is exponential of the sum of the integral. Oh God, there's a lot of nested quantities here. So this is an integral d of rho of E times E to the, oh God. Okay, so what we did here is we took the log of this and we Taylor expanded the log in order to get this crazy expression here. So what you'll notice is this, we now have sort of the exponential of an SFF. We're summing over these various different ends, but like what we have at its core is the SFF of a many body non-interacting system is roughly the exponential of Z for the non-interacting system. So if we do a cumulant expansion here, we're going to get the mean value of this Z, which we can calculate. And then the variance of Z is just the connected SFF, which is a line, an exponential of a line. We're going to have an exponential, exponentially increasing quantity here. So this is a completely different rough intuition for why there should be an exponential ramp for the SYK2.
Why is it chaotic?
Well, so it's the single body system, right? So the SYK2 is just a bunch of fermions which individually have random matrix energy levels, right? So the individual, it's a little bit confusing whether the system counts as chaotic. When viewed as a single body system, it's chaotic. When viewed as a many body system, it's integrable, right? Just like if you had a bunch of photons bouncing around in a Buminovich stadium or whatever, each of the photons is bouncing around a crazy chaotic trajectory, but at the same time viewed as a many body system, it's just Maxwell, it's quadratic, it's integrable. So it's, in my view, a very difficult semantic question whether this counts as integrable or not, but viewed as a single body system, it is. The single body SFF is going to be linear and the many body SFF is the exponential of that. So it's an exponential function.
I see. So should I think of each single particle as a sector in your language?
So I definitely thought about that and I've tried to make that like a precise thing. I wouldn't go that far, but I would love it if you went that far and made it work.
I see.
Because yeah, it definitely feels like there should be some connection where like after more time we can resolve more occupancy numbers, and each of these occupancy numbers becomes like a conserved quantity. So we have more sectors the more time we resolve. It definitely feels like that should be an intuition somewhere, but I haven't been able to like really nail that down.
Okay, I see. Thanks.
All right, any other questions? Actually, I was curious, can you pull up that formula that you derived with the return probabilities?
Hold on, give me a second here. You mean this one?
Right.
Yeah.
So I missed this. Is this something that I should expect to be true for any generic non-integrable system with some conservation laws?
So we have a few assumptions going into this. And the most important assumption is that the different sectors should be independent of each other. And we're able to come up with one class of systems which violates that, which is systems with spontaneous symmetry breaking. Each sector is kind of going to look pretty similar to the nearby charge sectors. Right, because you can kind of have charge in the, in the C, in the whatever you call it, in the condensed thingy. So each sector can look very similar. So actually, spontaneous symmetry breaking systems do not follow this law, and they have a related law which Brian and I worked out, and it's on the archive if you're interested. So that doesn't follow this, but systems where there's no particular reason to think the various sectors should be related or be similar, which seems to include hydro systems and seems to include spin glasses, and we think includes just about everything except spontaneous symmetry breaking systems. We should expect this to be true.
Right.
Again, and also we're assuming chaos within each sector.
And remind me again, what was f of e?
F of e is any function you want, right? So f, the SFF is defined in terms of f. So for a lot of people, we'll just set f equal to 1, a constant 1. A lot of people set it equal to e to the minus beta e.
Beta. Right, okay.
But it's often very conceptually helpful to set it equal to a Gaussian if you want to like focus in on the, is there level repulsion in this specific region? You have a Gaussian centered in that region or something.
Right. So I'm used to seeing it in terms of f of e being e to the minus beta e.
Yeah.
So
yeah.
then that's
we made up this notation with the f because we wanted to set f to be a Gaussian a lot.
Right. And where that beta is different from the beta you have. But is this the only place where the actual inverse temperature enters, or can it?
Yeah.
Otherwise, there's no temperature dependence.
The inverse
anywhere.
temperature only shows up here. Yeah. There's no other place where it shows up.
I see. All right. Are there any further questions for Mike? Well, if not, well, let's thank Mike for a engaging talk.
Okay.
And yeah, thank you.
Thanks a lot for having me.
All right, let's stop recording.